Principal Components Analysis, abbreviated PCA, for analyzing data extracted from a questionnaire or a survey. In this presentation, description of the PCA will be provided, and the common uses of the PCA will be mentioned, and the assumptions that have to be fulfilled before performing the PCA will be listed, and a short description how to input the data into one of the statistical software, and finally how to interpret an output from a PCA. Principal component analysis is a multivariate statistical techniques or a method that deals with data that consist of multiple variables or multiple items. It is an unsupervised statistical method. The objective of performing PCA is to reduce the number of variables in a data set. So it is dimensionality reduction method. It aims to reduce larger number of variables that is extracted from a questionnaire or a survey. Variables are items or questions. The objective is to reduce this large number of variables into a smaller number of variables that are, or a smaller number of variables grouped together, and these groups are called principal components. So the objective from performing the PCA is to reduce the number of variables and arrange these variables into groups called principal components. These components explain most of the variance in the original variables or data. Items within these components or variables or questions are correlated. The overall objective from performing PCA is to have a large number of items or variables. Try to reduce that number by grouping those items or variables into components. These components or variables within these components are correlated to each other. So what are the common uses of PCA? When a researcher starts to design a new questionnaire or an instrument or a scale, then a PCA is a useful statistical method. The objective of performing that method is to check if all or some of the items load into construct. If some of the variables are not sufficiently representative of the construct or the section within the survey or the instrument or the questionnaire, then remove those variables from the measurement scale. So PCA can be used to when designing a new questionnaire to check which items loads into certain sections or construct within a questionnaire, and those that they do not load to this construct or they do not correlate with the variable within that construct, then remove that item or variable. The second use of PCA is to reduce the number of variable in a construct. So it is called construct PCA. if a construct consists of, let's say, up to 12 variable, then PCA can be performed to find out what variables within that construct, which is part of the questionnaire, that are highly correlated and represent the construct. The third use of the PCA is to shorten questions to be included in the questionnaire. Shorten these items or questions or variables into fewer items. So another objective is reduction. So if more than one item measuring same construct, then remove that item, and that will help to design a scale or an instrument that can be accomplished and completed by participant. So what are the assumptions that have to be fulfilled before performing PCA? The first assumption is that multiple variables are measured at a continuous level or ordinal. So the data or the responses collected from participant completing the questionnaire, it can be an ordinal based on 5 Likert scale from 1 to 5, or 7 or 9, and so on, or the responses can be a continuous variable. So there should be a linear relationship between all variables if they are continuous. PCA is based on Pearson correlation coefficient. The method also can be used for ordinal data such as Likert scale. Linearity can be tested using a matrix scatter plot. The second assumption is sampling adequacy. There have to be enough number of participants. There have to be 5 to 10 participants per question or per items as a minimum sample size. Using rule of thumb, 10 participants per question can be considered. And the way to check, or the method to check whether there is a sampling adequacy, is to perform a Kaiser-Meyer-Olkin sampling adequacy that will measure the sampling adequacy for all overall data sets. The third assumption is that the data should be suitable for data reduction, sufficient correlation between variables to reduce variable to a smaller set of components. Though there should be a correlation between items, that correlation has to be within a certain values from 0.3 to 0.8. The Parlet test of sphericity can be performed to test this assumption. The fourth assumption is that there is no significant outliers, and the fifth assumption is independent variable are correlated to each other. Another assumption is that principal components are assumed to be independent of each other. And finally, there should be a homoscedasticity in which the variance of the data is constant across all levels of the independent variables. In this slide, a print screen from a SPSS software has been inserted here. When performing PCA in SPSS, the following boxes need to be ticked. First of all, the correlation matrix, tick for the coefficient for correlation and the significance level for correlation. the determinant, which is an important values for testing the data and whether it is enough to be used for performing PCA, and also tick for the KMO and a Bartlett test of sphericity for sampling adequacy. The next slide gives options for selecting the method for analysis, which is the principal component analysis, and the eigenvalue is selected to be greater than 1. For performing the PCA, the method for rotation has to be decided in advance. There are two types of rotation. That's depend on the variable, whether they are correlated. If the variables are correlated, then the direct oplement will be used, or the pro max. When the variable are not correlated, then the method to use for rotation is orthogonal, and there are several methods: varimax, equimax, and quantimax. The output that will be generated from the PCA analysis, there should be important things to look for. There is no missing scores. To check for the correlation coefficient, which is the R, the Pearson correlation coefficient, the value for determinants, and the KMO and Bartlett test for sample adequacy and sphericity, the setting for the eigenvalues, the total variance, the scree plot, the values for communalities, and the rotated matrix, with finally the table for the component transformation matrix. So this is a table extracted from a PCA analysis in which a correlation matrix has been generated for 9 items, item number 1 to 9, and the correlation between pairs of these pairwise of these items is given here, with statistically significant values shown here. And as shown here, that there is a perfect correlation between item 1 and item 1, and with item 1 and 2 the value is 0.65, and with item 5 and 1 it is 0.02. For the correlation values need to be, which is the R, need to be less than 0.8 and greater than minus 0.8, and the determinant has to be greater than 0.40 and 1. The next slide shows an output for the KMO and Bartlett test. The value need to be for sampling adequacy to be greater than 0.5, and ideally anything greater than 0.5 will be acceptable, but the higher the better. The p-value should be less than 0.05, and for the eigens values when performing the PCA, the eigenvalues set at as greater than 1. So what does this eigenvalues mean? It represents the variance explained by each principal component. Higher the eigenvalues, the more variance is explained by the principal component. Here is a table extracted from a PCA analysis, as shown here, the total variance explained. There are here 8 items, and as shown in the section here, extraction method, principal component analysis, there are 8 items, and those items have been grouped into 3 major components, component 1, 2, and 3. Component 1 explains 27.3% of variance. The second component explains 25.7%. The third is 19.1%. The 3 component explains 72.2% of the variance. The next slide shows the scree plot. Scree plot assists in determining the appropriate number of principal components to retain or to obtain from the analysis. It is used to visualize the eigenvalues and identify the point at which the curve levels off, suggesting that the optimal number of components to retain. Here in this graph, it shows that on the x-axis is the component number, on the y-axis is the eigenvalue. There, the cut point for the eigenvalue is 1, and there are 3 major components, 1, 2, and 3. The next slide describes a terminology called communalities, which is a table generated from the PCA analysis. Communality is the proportion of variance in each variable that is retained in the principal component. So the value for the communality ranges from 0 to 1, as shown here in the table. The first item has a communality value of 0.8, the second 0.7, and so on. The next slide describes factor loading. Factor loading is a measure indicates the strength and the direction of the relationship between variables and principal component. The higher the factor loading, the stronger the relationship. Factor loading is a coefficient, and the cut for factor loading as a rule of thumb is 0.3. Some people use 0.4, and some people become more stringent and use 0.45. So aim for a high value, which is 0.9. As shown here in the table extracted from a principal component analysis using a varimax method for rotation, these 9 items has been grouped into 3 components, component 1, 2, and 3, as shown in this rotated component matrix. The first component have 3 items. These 3 items, item 4, 6, and 5, loads together on that component, and the loading factor score is 0.88, 0.7, and 0.7. So those 3 variables loads into that component. For the second component, there are 3 items. Item 1, 2, and 3 loads into the component 2, and the value for the factor loading is 0.9, 0.8, and 0.79. And finally, the third component have 3 items loaded into it. Item 7, 8, and 9. With the first one is 0.89, 0.7, and 0.65. All these 3 items load into the component, principal component 3. So the overall analysis from the PCA has managed to group these 9 items into 3 components. Another output that can be generated post PCA is the component transformation matrix. The component transformation matrix will look at the correlation between component number 1, correlation with 1, and 1 with 2, and 1 with 3. So if the components correlate to each other, then this will help in determining the rotation method. Then use oblique rotation, whether it's direct, oplement, or pro-max. When the components are not correlated, then use orthogonal rotation, such as varimax, equimax, and so on. And how do we determine the cutoff point for correlation or no correlation? A value of correlation between 2 components of greater than 0.32 indicates correlation between the components. If you find this video useful, do subscribe to the channel, leave any comment in the indicated box and activate the notification bell to receive the recent and latest release into the channel of several different video clip, and click on the like icon and share the video link with others so the channel can expand and improve to include a large scope of different statistical method and how to analyze data using several different statistical packages such as SPSS, Excel, Stata, Jamovi, Statistics, GraphPad, Prism, GPower, Python, and RevMan. If you are a student or a researcher and you have a data, whether it is quantitative or qualitative, and you want to perform statistical analysis on that data using any of the softwares listed here, whether it's SPSS, Excel, Stata, Jamovi, Statistics, GraphPad, Prism, RevMan, GMP, Python, then do contact me to arrange for either a one-to-one private tutor session or a training course on any of these statistical packages. My contact details are given here, so don't hesitate to write to me or email me if you need a private one-to-one tutoring or a training course.